he did it with more hypotheses, with less hypotheses, because the right notion between these results is not PAUS. It's a notion of upper LP3 estimates, or what William calls AP, and so he did it with this notion. So first, just as a reminder, we say that a Banach space is quasi-reflexive if the image of the Banach space by the canonical map into its bidual is of finite codimension in the bidual. So this is quasi-reflexive. And we denote ik of m. It will be all pairs of elements of mk, but we assume that they are interlaced. That is to say, like n1 smaller than n1, smaller than n2, etc. So the pairs of interlaced elements, and we can see that it can be identified with m to the power 2k. So it's really, you can see it, and this will allow us, of course, to use Ramsey theorem again. So the result, you take a quasi-reflexive Banach space X that has an equivalent norm that is PAUS, then you can find a constant lambda such that for all integer k, for all maps defined on the Hamming graph of height k into X, you can find a subgraph, and this time the concentration is not for all pairs, it's just for all pairs of interlaced elements, such that f of n bar minus f of n bar in norm is less than or equal to lambda times the LP norm of the directional Lipschitz constants of f. And this property for such a lambda, we denote it HICPD, where the I this time doesn't mean full, it means interlaced, because we only consider interlaced elements. And of course, we can take off the D, and we have a less strong notion, just we bound from above by lambda times the Lipschitz constant of f times k to the power 1 of the p. Okay, so this notion of interlaced concentration indexed by D, if we write it with quantifier, we have that. And we can see that since ik of m can be identified with m to the power 2k, we can apply Ramsey theorem. And so it is equivalent to the fact that for all integer k, for all Lipschitz map, for all subgraph, you can find only one pair of interlaced elements, such that you have your inequality. And of course, two elements that are interlaced, they have empty intersection. So this implies that for all k, for Lipschitz map, for all subgraph, you can find one pair of elements in your subgraph with empty intersection, such as you have your inequality that we denote just with a star. And this concentration, we will denote it just HC, because we don't assume interlaced or all pairs. And it seems easier to check. If you want to check that a space has concentration, it's easier to find two elements of empty intersection than two interlaced elements. So you have that interlaced concentration with some lambda implies this concentration with the same lambda, but in fact you can prove that this simple concentration with a lambda implies the interlaced concentration with a, but we lose something on the constants, it's multiplied by 2, but it's okay. These two notions of concentration are the same. And to see it, well, two elements that have empty intersection, they can be in a finite number of positions. For example, they can be interlaced, all the elements of m bar can be smaller than the elements of m bar, etc. But you have a finite number of possibilities. And so this concentration, just HC, it tells you that you can, for all integer, for all Lipschitz map, for all subgraph, you can find one position and one pair of elements in this position that will denote P indexed by I to the power k of m, such that you have your inequality star. But now, when you fix a position, you can apply Ramsey theorem again, so you can change quantifiers. And this tells you that for all k, for all Lipschitz map, you can find one position and one subgraph, such that for all the elements in the subgraph that are in this position, then you have your inequality star. And now that we exchange the quantifiers, we just have to take two elements, n bar and p bar, that are in this position, but we assume that all the elements, all the coordinates are far away from each other, just all of them. And this allows you to find an element n bar in nk, such that at the time you have that n bar and n bar are interlaced, and at the same time you have that the elements, the couple n bar and p bar, has the position at the beginning. And this is because you left enough space between your coordinates. And now you just have to apply the triangle inequality, so it gives you the 2 lambda instead of lambda, but it's okay. So these two concentration properties are the same. Now we can do some similar remarks with the theorem of Lancian-Lacha than the theorem of Calton and Rivoni. So we said that if a Banach space had full concentration, then we couldn't ellipses embed the Hamming graphs, and the contradiction was obtained with elements that were at distance k. But elements that have empty intersection, they are at distance k. So we still have that if you have concentration, then we can't ellipses embed the graph into the Hamming graphs into X. And we also have that if you cause Lipschitz embed a space to Banach space that has concentration, so we can index it by D or not, it's the same, then the embedded Banach space also has this concentration. But we said that full concentration implied reflexivity, but this time we don't have that the concentration implies quasi-reflexivity, and that's what we will show later. So if we summarize, we know that we can't ellipses embed the Hamming graphs into a quasi-reflexive PAUS-able Banach space. Okay. But by our Onesie theorem, we know that every separable metric space can be by Lipschitz embedded into C0 with a universal constant. So this means that we can ellipses embed the Hamming graphs into C0, and C0 is PAUS for all P. So it was a natural question to ask if whether or not we could find a space between those two that had concentration. And the result is yes. So if we take a sequence Xn of Banach spaces and we ask them to have the interlaced concentration, but all with the same constant lambda, and this time we have to index it by D. We have to take directional Lipschitz constants. Then we can prove that the LP sum of these Banach spaces has this interlaced concentration, but we lose something on the constants. It has this concentration with constant lambda plus 2 plus epsilon for all positive epsilon. And just as a reminder, the LP sum of the sequence Xn, just the sequences Xn where all the elements Xn are in the Banach space capital Xn, and the norm that we put on this sequence is the LP norm of the norm of the elements of the sequence. And if all the Banach space are the same Banach space X, we'll denote this LP sum just LP of X. So if we prove this result, now we know that the James Banach space J, that is isometric to its bidual but not reflexive, it is quasi-reflexive and to a USable. So we know by the Lancian-Lacha result that it has concentration indexed by 2. And now we can apply the theorem, and we have that L2 of J also has this concentration property, but this time it's not quasi-reflexive, of course, because the quotient of this space, of the value of the space by L2 of J is equal to 2. And to prove this result, we do it in two steps. The first step, we consider finite sums, and after we treat the rest. So to do the first step, we just have to show that if we take two Banach spaces with interlaced concentration with the same lambda, then the P sum of these two spaces has interlaced concentration with constants lambda plus epsilon for all epsilon. So we can already see that the loss of the constant is not when we consider finite sums. It will be when we take the rest. So of course, if we have this result, we have it for finite sums. And to prove it, well, we have to introduce a Lipschitz map, H, that goes from the Hamming graph of ik into x. And we can see it as a couple where f goes into x1 and g goes into x2. And we just take an epsilon prime that will be small enough at the end. The idea is to go on subgraphs where the directional Lipschitz constants are the smallest possible. But for example, the first directional Lipschitz constant of f and the first directional Lipschitz constant of g would be small on different, very different subgraphs. So what we will do is that we will make them small enough, the smallest possible, but at each time we'll stay in the subgraph that we introduced before. So we define a quantity L1, so it will be the smallest Lipschitz constant in the first direction of the map F. So just as a reminder, H1 of M1 was the pairs of elements that differ on the first coordinate, and N1 was smaller than M1. So we take the infimum of all subgraphs and of the first directional Lipschitz constant of f on this subgraph, and this gives us a subgraph where the first directional Lipschitz constant of f can be bounded from above by alpha 1 plus epsilon prime. And now we will stay in this subgraph, and we'll do the same for the first directional Lipschitz constant of g. So we introduce a beta 1, the infimum over all m1 prime, subgraph of m1, the supremum over g of n bar minus g of n bar, on where n bar and m bar are pairs in h1 of m1 prime. And this gives us a second subgraph, including the first one, where the first directional Lipschitz constants of g can be bounded from above by beta 1 plus epsilon prime. And this time, we'll do the same thing, but with the second directional Lipschitz constant of f, but staying into the subgraph that beta 1 introduced. And we do that until we introduce a finite subgraph denoted by nk prime, where the directional Lipschitz constants of g in direction k can be bounded from above by beta k plus epsilon prime. And now the key of the proof, that's why we took the directional Lipschitz constant to be the smallest possible. It will be to show that for all j between 1 and k, we have that alpha j to the power p plus beta j to the power p is less than or equals to the directional Lipschitz constant of h. So h was the map into the sum to the power p. So to do that, we assume the contrary, and then we can find a j and a positive eta, such that alpha j minus eta to the power p plus beta j minus eta to the power p is bigger than the Lipschitz constant of h in the direction j to the power p. But now, by definition of the directional Lipschitz constant of h in the direction j, we know that for all pairs of elements, so that differ only on the coordinate j, and when we assume that nj is less than nj, we have that either f of n bar minus f of n bar in norm is less than or equal to alpha j minus eta, or either we have that the norm of g of n bar minus g of n bar is less than or equal to beta j minus eta. And that's when we see the interest of taking directional Lipschitz constant, because we make appear this set aj of m cap prime, and this we said that we could identify it with m cap prime to the power k plus 1. And when we have that, we can apply Ramsey theorem. And Ramsey theorem tells you that you can find a subgraph of m cap prime to the power k, such that for all elements, all pairs of elements in aj of this mu m, you have that f of n bar minus f of n bar in norm is less than or equal to alpha j minus eta, or for all elements in aj of m, you have the over inequality. So you have the quantifier for all goes, this time it's 2 times. We have it 2 times. So now we can get a contradiction with the definition or either alpha j or beta j, because we defined it as to be the smallest possible constant, directional Lipschitz constant. And so now that we have this fact, it's over, because we can apply our hypothesis on x1 and x2, and it gives us a subgraph such that for all pairs of interlaced elements in the subgraph, we have that f of n bar minus f of n bar is less than or equal to lambda times the LP norm of the directional Lipschitz constant, but the directional Lipschitz constants can be bounded from above by alpha j plus epsilon prime. And we have the same with G, where they can be bounded from above by beta j plus epsilon prime. And now we just have to make epsilon prime to be small enough, and with the fact we have the desired inequality, so that the norm of h of n bar minus h of n bar is less than or equals to the lambda plus epsilon times the LP norm of the directional Lipschitz constant, and for all interlaced pair of elements. So this is the proof for the finite sums, and now we can prove the results for all the sums. So if we take a map, so a Lipschitz map defined on the Hamming graph of height k into x, we can write it as a sequence of maps, Lipschitz maps, and we take as before an epsilon prime small enough. So first, we can note that the map phi defined on x into LP that sends a sequence of x on the sequence of the norms is 1 Lipschitz, and so the directional Lipschitz constants of phi composed with f is less than or equal to the directional Lipschitz constants of f. And since phi composed with f is defined on nk and goes into LP, when we look at the proof of Calton and Randrian harmony, when we are in this special case, we know that we can find an element u in little LP and a subgraph such that for all the elements of the subgraph, we have that the norm of phi composed with f of n bar minus u is less than or equal to the LP norm of the directional Lipschitz constants of phi composed with f, but we bound from above by the Lipschitz constants of f up to an epsilon prime. Now this gives you an element n such that the LP norm of the rest is less than epsilon prime, and with this n we can denote pi n to the projection that goes from x onto the LP sum of the first n Banach spaces. And now that we have, when we have the sum of the first n Banach spaces, we can apply our proposition, and this gives you a subgraph such that for all pairs of elements that are interlaced in the subgraph, you know that pi n of f of n bar minus pi n of f of n bar in norm is less than or equal to lambda plus epsilon times the LP norm of the directional Lipschitz constants of f. So this is your proposition, and now you have to deal with the rest. But by choice of n and the fact that the LP basis is one unconditional, we can both from above the norm of if I denote the identity I minus I n of f of n bar by up to an epsilon prime by the norm of this quantity phi of f1 bar minus u, and we saw that we could bound from above the quantity with phi composed with f of n bar minus u, and so when we put this inequality with the first one with the finite sums, when we directly get that we have that the norm of f1 bar minus f1 bar is less than or equal to lambda plus 2. The plus 2 comes from the fact that the inequality just above this one, we lose a lot of information in this inequality, so it gives us the plus 2, so lambda plus 2 plus epsilon times LP. LP norm is the directional Lipschitz constant for all the interlex pair of elements, and this is exactly what we really wanted to show. So we have the proof of our theorem, and I have time for a few remarks. The first one is, at first we didn't know if the concentration with directional Lipschitz constant was the same than without considering it. It seemed unlikely, but we didn't know. And in fact, we could find a space that has full concentration, but reflexive in particular, full concentration indexed by P, but it doesn't even have the simple concentration indexed by P and D. So these are really not the same. And we could also find a space that has full concentration indexed by S and D for all S between 1 and P, but that does not have a property H, concentration, simple concentration indexed by P. And for another remark, I need to define free space properties. So we say that a property P is a free space property is when you take a Banach space X, you take a closed subset M of this Banach space X. It is enough that two of the spaces between X, M, and the quotient of X by M have property P, so that the third one also has it. And we could prove that none of those concentration properties that we introduced before is a free space property. And to do that, we consider Carlton-Peck spaces ZP. They have the particularity of, we can find a subspace M of this spaces ZP, such that M is isometric to LP. The quotient ZP by M also is isometric to LP, but ZP is not isometric to LP, and in fact, it doesn't have any of the concentration properties. And now I can say a few words about the case P equals infinity. So to do that, I need a few definitions. So first, we denote M to the power less than K like this. It will be the sequence of the finite sequence that have K elements or less. And we will say, so a tree will be just a family of X indexed by these sequences of K elements or less. And we'll say that such a tree is weakly null if when you fix an element, so a finite sequence that has K minus 1 elements or less, if you look at the sequence X indexed by this sequence n bar and you concatenate it with some n, and when you take the limit in n, this sequence is weakly null. So that's what weakly null tree is. And we will say that the Banach space is asymptotic C0 if you can find a constant C such that for all k and for all within a tree indexed by these sequences of height k or less, you can find a subgraph such that for all the elements of the subgraph, for all scalars, family of scalars A, you have that the norm of the sum from j equals 1 to k of aj times x indexed by n1 and j is less than or equal to c times the maximum of these absolute norms of absolute values of aj. So this is asymptotic C0, and when I said that Ryan Cozy used the notion of AP or upper LP3 estimates, it was the same thing, but instead of considering the L-infinite norm of the family A, we look at the VLP norm of this family. So we have the notion of asymptotic C0, and we can define similar properties. When we looked at the full concentration definition, or all the definition of the concentration, we had lambda times the LP norm of the directional Lipschitz constant. And this time, when we look at the L-infinite norm, we know that the Lipschitz constant of F is the maximum of all directional Lipschitz constants. So just if we write it, we have this definition because even the k to the power 1 of a p becomes 1. So we say that it has full concentration for p equal infinity if for all k and for all Lipschitz constants, we can find a subgraph such that for all pairs of the subgraph, we have that the norm of f of n bar minus f of n bar is less than or equal to lambda times the Lipschitz constant of f. And since the Lipschitz constant of f is just the L-infinite norm of the directional Lipschitz constant, looking at directional Lipschitz constant has no meaning anymore because these are the same properties. And of course, we can define interlace concentration and just simple concentration the same way. And when we look at the case p equals infinity, we have stronger obstruction because this time we just don't have only that we can't Lipschitz embed the graph. We know that we can't Lipschitz embed the Hamming graphs into X, where we say that the graphs embed into X if we can find two non-decreasing functions, two moduli, rho and omega, and a family of maps indexed by k that goes from nk to x, such that you ask that the limit of rho at infinity is infinity, and you ask that for all t, you have that omega taken in t is finite. And finally, you ask to have this inequality, so that for all k and for all pairs of elements in nk, we ask the norm of fk of n bar minus fk of n bar to be bounded from below by rho taken in this in the Hamming distance between the two elements, and bounded from above by omega taken in the Hamming distance between the two elements. So this is a really less strong property that Lipschitz. We ask it's a way stronger obstruction to the embedding of the graphs. And Baudier, L'Ancien, Motakis, and Flumprecht prove that this property, full concentration with p equals infinity, is equivalent for Banach space to be reflexive and asymptotic C0. And they also prove that if you take X Banach space that is quasi-reflexive, asymptotic C0, then you can prove, as for the finite case, that X has a concentration indexed by infinity. And in fact, you can also prove that concentration implies asymptotic C0. But since we don't have this notion of directional Lipschitz constants, we can't have the same results that we have on LP sum for when P was finite. So it's still an open question to know if the concentration implies quasi-reflexivity. We don't have any counterexample. And I finish this talk with a few open questions. So we know that if a Banach space X coarse Lipschitz embed into a Banach space that is reflexive and PAUS, and just AUSable, you know that it is reflexive, but we don't know if that means that it has an equivalent norm that is AUS. It's still an open question, I think. Another question would be to know if the theorem for LP sums could be improved so we don't have such a loss on the constant. We'd like to keep, if we could keep it, like just have interest concentration with lambda plus epsilon for positive epsilon. It's unlikely that we can do it, but if we could do it, then we would be able to find a space that is non-AUS and that has a concentration property, because for now, all the spaces we have that have concentration, they are AUS up to renorming. And finally, what we did would be a special case of this. If we take X, a P-AUS Banach space, we ask it to be complemented in its bidual, and we ask the quotient of the bidual by the self versus the space itself to be reflexive and PAUSable. So the LP sum would be a special case. Does this space X would have a concentration property? It's still an open question. Thank you for listening.
All right, so are there any questions? Chris?
Yes, I may have questions, maybe, but after the room, there are people in the room asking questions first.
So, okay, so go ahead, Gilles, if you want to ask a question.
So one first question that crossed my mind when the Carlton-Peck spaces were mentioned. If I understand correctly, they don't satisfy the concentration properties. But could it be a general statement somehow when you have an actual twisted sum, say, let me take P equal 2, an actual twisted sum of Hilbert spaces, is there any chance to show that it fails the concentration property unless, of course, the space is L2? Could it be a general statement?
Like twisted sum of, but with no more properties on it?
Yes, yes. I mean, that would be a quite ambitious problem, of course. But if you have concentration property on a twisted sum of L2, does it untwist the sum in a certain sense, in general? Is there any hope of something in this direction?
Maybe. I wouldn't believe it so much, but it's a possibility. Yeah, but like this, I'd say no, but I could try, yeah. Thank you.
Okay, you have people around you in Texas A&M who knows this business extremely well. I mean, so that's the right place to think about it. Another question, which is maybe a little bit folklore, but if I understood well at the end of your talk, the question is really to know whether quasi-reflexive and asymptotically C0 would be equivalent to HC infinity, right? If you can imply HC infinity implies quasi-reflexivity, that would be an if and only if, right?
Yeah, exactly.
And I was wondering whether topological complexity can tell you anything about this. That is, I would expect HC infinity to be a Borel property in the sense that is well known today. I mean, in the collection of the set of separable Borel spaces. Is it so or not? Maybe some people in the audience have an immediate answer. Is it so or not that quasi-reflexive and asymptotically C0 is Borel as well? That is, or is quasi-reflexivity inducing some co-analyticity? I mean, the question could be answered already. I don't know. Maybe somebody knows, or maybe you know.
Thomas says it's not clear because he can't hear you.
Okay, Andrew Schack, I think, is in the audience, in the computer audience. I mean, he may know the answer as well. I don't know. But I mean, the question really would be, is there any chance to use descriptive set theory to distinguish between the two properties? That is, would you have some complexity, some ordinal complexity in the non-trivial elements of the bidual that would introduce some co-analyticity? Maybe there is no hope, but immediately I don't see whether it's hopeless. So, I mean, again, you have people around you who can be good people to talk with about this.
Yeah, thank you for the idea. We look at that. Thank you.
Okay, Andre. Good luck anyway, and hope to meet you in person one of these days. I mean, when
Thank you.
virus permitting. Thank you for this nice lecture.
Thank you.
Bill, I think you had a question. I saw that you raised your hand. No. Maybe it was just clapping. So, other questions? Chris, you had a question? Oh, yeah, come if you can come here to ask a question.
Well, I still just thinking how to formulate it.
Okay.
Let somebody else up.
Anybody else with a question in the remote audience? Maybe I have one. So you talked about LP sums, but if you take capital LP sums, can you say anything?
Well, we don't know because we use strong properties of a little LP, and when we take capital LP sums, if you have only one space, if it's not super reflexive, then the capital sum of X is not a US. And
Right.
we think it doesn't have concentration, but we don't know it for sure. And we're trying to look at that.
Right. Okay. Any other questions?
So I guess the question would be, maybe I missed it, but do you have a conjecture for what these concentration inequalities for the finite P case would characterize in the asymptotic linear world?
It would be nice to prove that we have concentration if and only if we can't ellipsis embed the Hamming graphs. But we take k to the power 1 over p, but if we take over maybe a logarithm or things like that, maybe we lose some concentration. So it would be nice to show it, but I don't know if we can.
Thank you. All right, one last question. So if not, let's thank Audrey again.
Did everything go well? You asked them whether.
Yes, let me stop the recording.